have total 6 degrees of motion, degrees of freedom in motion, 3 translation and 3 rotations. And yes, so at the max 6. So please keep in mind, there should not be any doubt here. It's unconstrained. Similarly, if you start putting constraint, then we can remove one by one, and at the max, what you can remove is 6 degrees of freedom by using these constraints, point contacts or contacts. For instance, here is one of the example, and suppose if you want to place one here, the frame, this 3-2-1 configuration is enough. So this is one of the way. There are a lot of other possibilities, so that we can check later, or you can even think about it. So 3 contacts I mentioned earlier. Precisely what you can do is, once you have 3 contacts, you can define a plane, right? And it's a unique plane. It's going to be unique plane. That's very important. So once you place this body, it's going to rest on these 3 contact points, and it will move in plane defined by these 3 contact points, right? So what happens if you don't define it? It tries to choose its own 3 points, right? And those will be the asperities on the surface, right? On the 2 surfaces, reference surface as well as on the rigid body. And in that case, we don't know. So that's the reason we may not be able to control it, or we may not be able to determine it exactly where it is. But if you define these 3 points, these things will be very much in control, and we can adjust this point and we can manipulate the body, right? So once it's there, like it's placed, right? So from the top, if you place the body, it's resting on this surface. Now what we do, we move towards this direction. What happens? Then it makes contact here, and then further pushing, so maybe it will rotate and it will make these 2 contacts, and this will define a line contact, right? And again here, this is unique. Do you think there will be any other point where it will make a contact? Not possible. So if you maintain these 3 contacts at the bottom surface, and if you keep pushing, it will make a contact 1 point, and it may rotate, and then it will make contact another point, and that's it. Because otherwise it will start fighting with the other 3 constraints you have at the bottom. So 3 plus 2, 5 removed. And what is possible? It can still move along this direction. So if you move further, it will make contact here and stop. So the idea is, if you have 3, 2, 1, 3, first you remove 3 degrees of freedom, then 2, then 1, and total, then you removed 6 DOF. And now it's a fully constrained. So now you can imagine that you have a rigid body and making 6 contacts, and assuming that these contacts are made, so assuming there is enough nesting force, you try to visualize if you can move it. So this is true for any rigid body. So maybe for like a regular cuboid, it's easy to understand, but then you can generalize, and then you can the idea is now you can take any shape, rigid body of any geometry, and if you follow these principles and remove these degrees of freedom with the contact, later we call it constraints, you will be able to get desired degree of freedom by eliminating what is not required. So this is the idea about when we talk about the exact constraint design, or when we talk kinematic design or when we talk about degrees of freedom and constraints. Moving forward. So what we are saying, each time a constraint is imposed, the number of degrees of freedom is reduced by 1. It's an ideal case when you. So if a constraint is imposed and suppose the contact is one single point, of course we reduce the number of degrees of freedom by 1. And so suppose if your rigid body movement in z direction is constrained, so suppose any body take, and suppose this is your reference surface, and suppose it comes and then you make a contact here, right? So moment is here. It cannot move in this direction. So degrees of freedom in this direction is cancelled, no more. And what will be still there is 5 remaining of degrees of freedom. 5 DOF is still left there. So what are they? So if you have a surface and suppose body is resting somewhere here. So if I define axis, X, Y, Z, and the rotations, all the rotations, right? So we also talk about the rotations. What is not there is, so if you just take this point, this is Z constraint, right? Translation. So translate along Z is not possible. Along X, yes, it can slide. It can slide. Along Y, it can still slide. Along X, if you are talking about rotation, it can rotate. The entire body can rotate. Same with the Y and along the Z direction. So you still have 5 DOF left and 1 constraint. So so if we say exactly constraint, if the number of constraint is not more, or what do we say, that the same degree of freedom is not constrained more than once, then we say exactly constraint. And if that is the case, then number of constraints imposed and remaining degrees of freedom should be 6. If it's over constrained, then it should be more than 6. But in ideal case, it can't be more than 6. Of course, never less than 6. Right? If you do the analysis and realize that number of constraints plus remaining degrees of freedom is less than 6, it means there is something wrong in your analysis and maybe you are not able to see or recognize that. So better find it out. So now coming to the basics. So very simple example of putting a constraint. So in 2D we are talking about the pins, but we are talking about the point contact. So in general, if we have a point contact, or suppose a spherical ball resting on a flat plane, right? Resting on a flat plane, and there is enough force, nesting force provided. What happens? You impose 1 constraint and remove 1 degree of freedom. So a simple single degree of freedom constraint may be envisaged as infinitely rigid sphere, right? Talking about rigid objects only, pressed against an infinitely rigid flat with the frictionless interface. Why we are frictionless? Because we are allowing sliding and all other movements, right? What is the assumption that the contact is there all the time? So just remember, one point contact, one constraint, and that will be along the normal direction of the contact point, right? So a point contact imposes a single constraint, right? So I think very much clear here now. So along the z direction, this is constant. This is also one of the like notation. So for DOF, use solid lines, right? And for rotations, either you can use these rotation source, right? Or use double arrows. So along this axis, rotation can be by this circular thing, circular arc, or with the double arrows. If it's a constraint, then you use dotted lines. So here if you see in z direction translation is a dotted, but it says that it's a constraint. Similarly for the rotation, what you can do, dotted with double arrows. This is equivalent to saying rotation along this axis. Yeah, so this is just about some notations. What happens if you have two contacts, right? Dumbbell kind of thing, or any object if you take and you only make two contacts. So if you take a dumbbell and put it on a surface, flat surface, there will be 2-point contact, and the constraint will be, these are the constraint line, right? That's what we studied. So you can say C1 and C2. These are constraint lines, right? So what it does, if you visualize, what you realize that for this dumbbell, of course, along the z direction, the translation is constraint, right? As long as there is a contact, it cannot move up. But a pair with some distance, so there is a distance, and what happens? Perpendicular to the plane. So if you take this case, so along x, so this is the projection, but if you it's in 2D, but the rotation along x-axis, but you see that these two will not allow, so they will constrain this rotation along. So, and you can put double arrows. So x rotation, so translation and z and rotation along x-axis. These two are constrained now. Now think about the other motion along the x direction. It can slide easily. Y direction also it can slide. Z is constrained. Talking about the rotation, here you call it, you can give any nomenclature, theta A, theta B, or theta 1, theta 2, theta 3. So rotation along x is not possible. Rotation along y is possible, right? It can easily roll. It can roll, right? Or it can, so either it can roll or it can spin also, because you are allowing friction. What about the z direction? Z direction also possible. It can spin. You can rotate along that direction. So here, now what do you see? There are two constraints and 4 DOF. So many times you'll be asked to identify those degrees of freedom and also level them. What will the directions? Many times For simpler cases, it's possible to find this way. But if it's a complex geometry, then what you may have to find the directions, and which may not be parallel to any of this XYZ or your frame of reference or your coordinate system. It can be some oblique line, some line in space, right? And maybe on a surface, or may not be on the surface. So that also you have to identify. But so that's why it's very important that 4 plus 2 should not be less than 6, right? Something wrong. If you have this, if you are getting 4 plus 2 less than 6, then it's a problem. Something you have missed. But so what happens? So here you are just putting a dumbbell on a flat surface and making 2 contacts. Now you just assume a ball, a spherical ball, and you put on a V groove. So I have many examples here. Like earlier, I was explaining some of the designs here. So ball on a V, right? So yeah, just today morning I realized that it can be also like this tabletop. So moment you have this configuration, right? So if you put ball on a V like this, actually again you are making 2 contacts. And 2 contacts means you there are 2 constraints, and there should be 2 constraints imposed. So what are they? How to visualize them? So flat will be like, if I try to find the C, the constraint line, define the constraint line, it will be my constraint line, right? Suppose C1. Similarly, if I want to define, the other will be like, so this one will be C2. These are 2 constraints now imposed. These are the 2 directions. So if I ask you to, okay, let me, I think, I don't know how to get the eraser. Getting messy. Plane, yes. So these are 2 constraint lines, right? So if I see the motion for this ball, and assuming that this contact C1 and C2 are made, what are the 2 motions? So 2 constraints. It means 2 motions should not be possible, right? And those are along C1 and C2. So if you see here in the other diagram, and if you try to find, so if you say, so this is now the frame of reference, this is Y, and this is Z direction. X is out of the plane, right? So what you see, any constraint on YZ plane, you can equivalently say that they are constrained in YZ plane, right? So any 2 direction on the in YZ, any 2, right? So we are talking about the equivalence, right? So same thing happening here. So if you take YZ plane, so this is Y and Z. So any 2 directions, not necessarily it has to be like this, right? But we like this can be also one pair, C1, C2. In this case, it's like C1, C2. They are also equivalent, right? So what we say that in this case, if we put a ball in V group, it constrain the motion, both translation motion along a plane which is perpendicular to the V groove, right? So any plane, so if this is the axis of V groove, so any perpendicular plane, it cannot move, right? So to constrain, then what are the four dots? There will be four motions, right? So from here in 2D, we realize that there will be one rotation, right? So it means rotation is also possible because it can slide, right? It can rotate. You can see. So A is possible. Okay, maybe what we saw that this is a constraint. This is a constraint. X, it can translate, right? Along the groove. Along the groove, either it can roll or it can slide. Both are possible. If we are talking about rotation, is also possible. B, it can rotate, right? B is also possible, rotation along Y direction. Along Z is also possible, right? So all the three rotations are possible. But you remove these two translations. So if it's in a V group, you remove the translation along a plane which is normal to the V group. In the earlier case, it was one translation and one rotation. If it's on V, these are the translations. Right? So ways to constrain 2 degrees of freedom, but they are constraining differently. So two joined spheres on a flat dumbbell or one single sphere in a V. So they also provide two DOF constraint or two constraints. What happens if we connect another sphere, right? So now we are putting the third one. So by now you might have realized that one by one we are increasing the number of constraints, and as we increase the number of constraints, the degrees of freedom constraint will also increase, or degrees of freedom for that body will get reduced. So in this case, if you put on a flat surface, it will make three contacts. So you can call it C1. So these are basically three constraint lines, right? So normal to the surface. So what you might have realized that is equivalent to what we mentioned today in the beginning, 3-2-1 configuration. So moment you make three contacts, it will be constrained in a plane. And what you realize here, that moment you have these three contacts, this body, like this body with the three spherical balls connected together, rigidly connected, what will happen? It can move along this plane. So what is the degrees of freedom here? It can slide in Y direction. It can slide along X direction, right? And it can rotate along the Z direction. That's possible, right? So X translation, Y translation, and Z rotation. And that's what we mean when we say that whether a body is constrained in a plane. So here is a 3-point constraint, and this is equivalent to saying that it's a constraint in a plane. Constraint in a plane. So when we say that it's a constraint in a plane, always remember we are talking about X and Y motion, translation, and rotation also. Rotation perpendicular to the plane, right? So we are talking about 3 DOF. Always remember. So whenever we ask, many times you may have a doubt we are talking about only translation. But if we say that it's a planar motion, then we mean three DOF and two translation along the plane and rotation perpendicular to the plane, right? Agreed? So again, now you can check the other 3 degrees of freedom and whether it's possible. So translation, so the constraint, these are the DOF. We are talking about X, Y, these are the translations, translation DOF. And rotational DOF is along Z, right? Which is perpendicular to the plane XY, right? So now the constraint. So as long as there are contacts made, right? So you can see Z is not there, Z translation, but the 2 rotations of the plane. So A, you cannot have without removing the contact. Same way, so in this case, C1 and C2 will ensure there is no rotation along the x-axis, right? When you are talking about B, rotation along y-axis, so if you assume that C1 and C2 are along y, then okay, they will not constrain any rotation along y-axis. But if there is the offset, so if the C3, which is offset from C1 and C2, so there is a line connecting C1 and C2, and if you take this point, there is a normal distance, right? And because of that, it will not allow this rotation B, which is along y-axis. So 3-point contact, 3 constraint, and you have only 3 DOF, which is in plane, defined by those 3 contact points. What are the other design? What are the other 3 DOF constraint contacts? What you can say? So if you have a sphere in a trihedral hollow, trihedral hollow is, so you just invert a tetrahedron. So tetrahedron is like, right? And then you have another. So this tetrahedron, right? All triangles only. If you just invert, you make 3 surfaces, right? One at the back, and then you have surface, and this is hollow, right? So now if you put a ball here, in 3D it's difficult to make. So if you consider putting a ball there, it will have 3 contact here on this surface, and third on the other surface. So three contacts. So somewhere here, and here. So in 3D, right? C1, C2, and very difficult to project C3, right? So C1, C2, and C3. And if it's a regular tetrahedron, what will happen? They all 3 will intersect. So if I make a projection, what will happen? There will be okay, let me just erase. But you realize that C1 will be like, suppose here, make contact, and then you can extend. Same way you have C2 here, and C2, so they will intersect, C1, C2. And similarly, on the other side, you will have another from this back surface, this is C3. So they will all intersect here at this point, which will be center of the sphere. If it's a regular, if it's not regular, okay, these three can be skew lines also. So we'll talk about that. So in this case, what's happening is there are three constraint lines, but they are not aligned along X, Y, Z directions, right? They're maybe along the diagonal, or okay, so they are normal along the surfaces, the contacting surfaces, and passing through the contact points. So what will happen, all these three can together constrain all the translations. So now if you talk about X, Y, Z here, X, Y, and Z translation of this point, it cannot move. If you talk about this point, it cannot move along C2, it cannot move along C1, C2, or C3. So all together, if you are able to resolve the component, you realize that you cannot have a motion along X, Y, Z, all the three translation. Not possible. What is possible now is rotation along X possible, Y possible, and Z possible. Why? Because if you try to rotate at this point, what will happen? It will try to move along the normal at this point, along the perpendicular directions. And C1, C2, C3, they cannot constrain the body from moving normal to the direction, right? And that's why instantaneously, so at that particular instant, it can rotate. So in this case, there is no, it's not welded. So what will happen if you try to rotate? It will simply slide, right? So you can that it's a frictionless surface, so it can easily remove. Of course, if there is a friction, then there will be some forces, but it can slide, still slide. If the friction is high, so it will be dependent on the factors. So for the time being, for the analysis, what do we assume? That there are no friction. There is no friction, right, between the contacting surfaces, right? So I think it should be agreed. So what basically what you are doing here is, you are by doing this, you will be able to define a spherical joint, and also at the virtual point. It's a virtual, right? There is no joint there, but still it can rotate there. So it's even possible to do like so suppose some body, and suppose you want to rotate this body here, all the three rotation, you may define contacts here which are and surfaces such that they are normal. So these C1, C2, 3 are defined and they intersect here. So what happened at this point, body can rotate. So this is one case. Another case, if you have a dumbbell, and what you do differently here is, you put one ball on a V groove and one ball of flat. So what will happen? Again, you have two C1, C2, and then here is a normal. So I think I would leave this exercise to you and try to find how it what are those three DOF constraint and what are the three DOF, right? So one in V and one on flat. So we keep emphasizing one constraint body, 6 degrees of freedom. Number of contact points between the two rigid bodies equal to the number of constraints. So I think I showed you this example earlier, and maybe in terms of stability, precision, or whatever you call it, or deterministic design, you may realize now, okay, three-legged is better, right? For the obvious reasons, because you have C1, C2, and C3 defined. So you'll be also able to calculate the reaction forces also, the forces along the constraint lines. In this case, if I say what will be the weight distribution, you can't tell me. It's not possible. Or I think worst is if I say, okay, let's clamp it, and then tell me. So these are things which you can ponder, which you can just try to analyze and see yourself. If you are not convinced, we can discuss further. Okay. So if you are talking about machine guideway, so any lathe or any kind of motion system, if you are defining, but generally what we want to have is, this is the base and this is the slider. So what we want is, this should be able to move in this direction. Linear, right? Linear motion. So one dock only. So what we want is, it should be able to move freely along this direction, right? So this is desired motion, this translation. Right? All others should be constrained, right? So this roll, this pitch or departure, this movement along this direction, same way along this direction, should be all constrained. So if you see, I think earlier design, I think very good, because what they used to do is, on the machine base, you used to have only flat. So this is the base. On top, we'll have this V, or it may be other way around, right? Resting on V, and this side will be a flat. So these are called semi-kinematic design. What you can assume, that there is one contact defined here, one contact defined here, and then one contact defined here. And okay, then you have the other side also. So what happens if you, I think I'll pose a question. What happens if it rests on two of these? What will be the problem? Do you see any problem in that? And the top one will be like this only. I would like to check yourself and get convinced, okay, this is wrong and this is over constraint design and it will not work. This is preferable, right? So in the older design, is very much there. Of course, I think now we see these two linear guides, and the problem is most of them is over constraint design. And but it is still work. Why? I think those are the questions we need to answer, right? So just check. So if we use the principle of exact constraint design and move forward, this will be the ideal design. So you have two contacts here on this ball, two contact on this, and one contact here. So two balls in V and one on flat. 2 plus 2 and 1. So total remove 5. 5 constraints. and one dot, which is it can slide. So this is the I would say the basic one should start with, and then you develop and you can have the detailed design. So I would like you to think about it, X, Y, and Z. How the different direction or different motions are in constraint. So I'm not explaining you here now, but I would like you to see and understand and take it up later. So there you can see a lot of designs based on this principle, and then you can have like you can simply put 3 balls on a V. So bottom will have 2 V, but the top has 1 V and 1 flat, and it will give you the constraint you want. You will have only one rotation, which is perpendicular to the plane. So 5 contacts on a carriage, 1 dot freedom. And how it will be made? So on top you have 2 plus 2 plus 1, 5. At bottom you have 6, right? Because you want to have deterministic behavior with respect to the bottom one. And the way it's done, the 3 balls, although it will be loose balls, but if it rolls and if it doesn't slide, then it will give a one-off system guideway. So many designs in the labs or in the old designs, you can find this kind of configurations. Maybe we stop here for a moment. Here is just resting on a plane, right? This is the question. So you may have like 3 contacts here, here, and here what we are saying that. So what you have is V. So let's try to make it. So I have V, and then what we say, I'll make it little little deep, and then it's a flat, right? So this is now again my reference. So here you have one contact here, one contact here. Now let me choose another color. So what I can choose, maybe green one. So here you have C1 constraint line, and I'm just, so I should not put arrow, but anyway, C2 and C3. These are the constraints. Here the constraints are like this, and maybe like this and this, right? So C1, C2, C3. So maybe if I just reviews, I draw it's like dumbbell, C1, C2, and okay, another surface you have, and then you have this, right? So C1, C2, C3. Here, if I make it in projection, you make a projection. So this, right? So 1, 2, and then this line C3, C1, C2, C3. What else we can do is take blue, and suppose now we start running the reference. So this is X, this is Y, and this is Z, right? And of course you have 3 rotation involved. So this is case 1, case 2. Okay, talking about DOF in this case, degrees of freedom. What is there? It can translation, X translation is there. Y it can also slide. And you also talk about constraints. The constraint is Z translation. Okay, so translation, I think there is no problem. What about the rotation? X rotation. X rotation, C1, C2, and C3. All together, they will not allow. So, X rotation constraint. What about Y? Same will happen to Y also, C1 and C2, because along the Y direction you don't have, right? So, Y translation is, rotation is also constant. But Z rotation, this all can slide. So, you can have Z rotation. In the first case, right? In the second case, if you're talking about the DOF, right? And constraints. What you see here is, again, X translation. Now X translation cannot happen, because C1 and C2 together, it will constrain the motion, right? Translation motion, which is perpendicular to the plane of the V, which is your XZ plane. So it means X translation is not there here in this case. X, suppose Y is along V, right? So in this case, X translation is there, but in this case, X translation is not there. Y is along the V, so it can slide. It can have that rotation, translation. So Y translation is there. What about Z? Yes, X and Z both constrained. So Z translation. What about the rotation? X rotation is possible without removing the contact, right? It's along the axis of this one. So very much, even at those points it can, right? So it can rotate. So you have X rotation. Here, X rotation was constant. Here is happening. Huh? What happened with the Y? Y, because of this C3, it will not allow this rotation. So Y rotation is constrained. What about Z? Z can happen because you can just fix it, and this since it's just a one point contact, it can slide, so it can rotate. So Z rotation is free. Right? So 3 DOF here also, this is also 3 DOF, but directions, whether it's a translation, rotation, different, right? So different requirements. So depending on the application, you may like to go for one or the other, right? And that's very important to understand. What is your requirement? Whether you just want a movement in a plane, or you wanted to have a motion along the V direction, and whether you want to have some motion along the Z direction, also some rotation. So it all depends on the application. Okay, we'll try to move. Okay, now very interesting topic, and what we call it, the thermal center or insensitivity to thermal effects. What do you mean by that, right? So what happens in normal cases, if you you have any joints, or suppose if you have a plate and bolted to the base frame, and suppose there is any thermal gradient, heat source there, what will happen? There will be expansion, and if there is no heat source, so suppose it's just switching on and off, there will be expansion and then the contraction. So there will be a lot of thermal strain, right? So what happens, that the points on the plate, they will also move, right, with respect to each other. Of course, if it's not designed properly, if the joints will give up, you will have a lot of internal stresses develop, and that will also leads to failure or deformations. Okay, so in high precision systems, ultra precision system, that is not desirable. First thing is, okay, you want to avoid any thermal centers or heat source, or if you have, you try to make a way that it should dissipate it easily, right? So that's why we talk about thermal loop, right? Secondly, if there are in thermal things happening, the thermal strain developed, some deformation are happening, then you try to find a location which are insensitive to them, right? And that's why sometimes we talk about designed for insensitivity. We are not calling it sensitivity or insensitivity. Means those points will not move even if there are any thermal deformation there on the part. So in this case, suppose this is the functional point, what you want. Functional point means, okay, suppose if you have a very sensitive equipment and you don't want this point, or whether it's a lens position or any tooling position, you don't want it to vary a lot, right? So you mount it at this point. What do you mean by this point or functional point, or how to know that what is the good point where you should mount it, or insensitive point to the thermal effects, right? So suppose these are some of the locations you want to identify, and you don't want any movement. So what happens, if this is the body, if you have, this is the object, right? You just color it so that you can identify, right? So what happens if we have constraint line defined contact, right? So these are the constraint defined, right? So what happens if this is like, it can be just a pin also, right? But these are the contact points. So what happens if there are any thermal effects, body along this, what will happen? This will act as a reference, but things beyond this will expand along this direction. Things along this line, they will expand along this direction. So what virtually you have found out is this line is insensitive. Any location on this point is insensitive towards this expansion, right? But it can still have these deformations, right? Because the heat can lead to deformation in all the directions. So then you define another contact here. So what happens then? You can just define a normal, and what it says, along this will expand along the, and things will not expand along this one, right? So it means you get a point here, right, which is ideal point, and we call it thermal center, TC, thermal center, which is insensitive to this deformation. So by putting this location points or contacts, we can define where should be your thermal center, where it should lie. And this dotted line, they are just showing that if there is any thermal expansion, they will expand like this. But you can think about this point will not move, right? So placing location points in the plane of functional point allows expansion and contraction without changing of its position, right? And that's called thermal centers. So how to achieve that? So this is the basis, this is the concept. What you can do is you can just put a pin, right? In 2D we talk about pin, right? So, or you can call it double pin or whatever, right? On the base, and then you just make these contacts, and you may need to have enough nesting force. Some nesting force should be there. So you can see that if there is expansion, it will go in this direction, this direction, this direction, right? But not this point. This point is purely insensitive. Huh? Right. So this is called thermal center. So, okay, that's one concept, and maybe I think with various examples later, you will be able to appreciate that, why that is required, and what is the importance of that. So we talk about this exact constraint design or kinematic design. So, of course, we want to justify, and we really appreciate that, okay, there are some benefits. Of course, there is no free lunch, as some senior professor used to say, that many times it's a give and take, right? You do something and you lose something. So what are the benefits? Why we are talking so much about the kinematic design or exact constraint design? So the benefits, okay, what we are is a deterministic. So whatever you do, anything which is not working, any error there, you can precisely calculate. It's a deterministic. And if it's a deterministic, later you can always compensate by adjustment or by control, right? All these systems will work in a feedback control loop, right? So if it's a deterministic, you don't have to do just some adjustment and leave it and pray, okay, maybe may go away. But deterministic means you should be able to calculate and then make that adjustment, and you can bring it closer to the point, desired point, right? So in all these principles, what is the idea? If suppose this is error band, right? So suppose if you do any activity, you want to reach here, but you are always sort of plus minus. So okay, this is the error band you are talking about. Huh? The idea is this error, you can always define or divide into two: systematic and random, right? So suppose one idea is you try to squeeze it, right? You try to squeeze because this is what you want, right? And suppose want to squeeze here, right? Move here. So the idea is not to remove entire error and squeeze it to this region, but the idea is to remove the randomness. Because systematic, you can always compensate, and systematic is deterministic. So if it's a deterministic, and even if the error is this much, and suppose this part is systematic error, that's still acceptable, and this is the random. So you skew it to this level. So even if in the beginning you find that, okay, the error is so big, right? But you may not have to panic if it's a systematic or deterministic design. How to explain that is your table with the 3 leg, right? You have 3 leg and with the adjustment here. So you bring it anywhere, it will sit there, right? It's a stable, fairly stable, right? But the thing is, it may be tilted, but that tilting you can remove just by adjusting these 3 very precisely. But moment you have a 4, it's very difficult because the 4th one you try to adjust, you don't know which 3 is resting on. So you'll start rocking on the other 2. And then you keep adjusting. So it takes a lot of effort. So if it's a deterministic, you can achieve higher precision, higher accuracy, and that you can do only through kinematic design or exact constraint design. And that's what it's saying. Does not rely on probabilistic approach. When you have random thing happening, then you depend on this one. Probabilistic, or then you do all sort of your AI or curve fitting, all those things you do. But if it's a deterministic, you don't have to. Is lower cost for given accuracy. This is very contradictory. Many times you think, oh, higher accuracy means you have to put a lot of money. But if it's designed well, you may not need a very high accurate components or precise components. And that's what we try to advocate in the beginning itself, that precision can be achieved using less precise components if we use exact constraint design. Repeatable relocation to high accuracy, repeatability can be increased. So again, it's a deterministic, right? You know where you are going all the time, right? So suppose if you are in NCC camps and then you do the firing, it doesn't matter where your gunshots are going, but if it's a center around somewhere, then you can always shift your marker and then you can get a very accurate results. So that's the idea. Repeatability means you can achieve high accuracy. Wear does not degrade repeatability except over long term, right? So even if there is a wear, it will still be repeatable, right? Only over long term you have to adjust. So with the kinematic clamp I showed you earlier, that you can easily visualize. Changing dimension in one element due to thermal effects will not induce stresses in the other. That's also good part. If there is any change in one, what will happen to others? It will reorient, readjust automatically. Reasonably tolerant to dirt. So what we are saying is it's more or less like maintenance free, right? We don't have to worry about other issues later. So these are the benefits. What are the limitations? So yes, I think limitation you all are aware of, right? Because in case of table, you say, oh, 4 is better because, okay, it has a high You can put more load and it's stable. Yeah. So to some extent, we agree, but maybe that's the thing we have to do in design, right? We have to do the analysis and do the projection. So load carrying limitations will be there because now you are not using the entire surface, but many times you are limiting to functional points, right? So it can just a contact point. So if you use contact in machine design, you know that there will be stresses developed and there will be failure, right? So of course, the load capacity, a stiffness many times can be also very low because of the same reason. Low damping, again, same reason, because you are now limiting to localized contacts. You are not talking about the contacts over a large area. So how to get rid of that? Of course, there are different ways, and there are some, to some extent, you can do that. And so you don't depend on the point contacts, but then what you try to do is semi-kinematic approach. So you start with the kinematic approach and then move towards semi-kinematic. So what is semi-kinematic? So for instance here, so you know that this will work, right? This works in principle. This is what you want, right? C1. But this is a contact, and of course it's infinitely rigid, so it will not happen, right? So of course then there will be some dent and there will be contact stresses developed, so that will lead to failure. So in case, what we do, we try to spread it over an area. So then we start making this kind of features, right? And do this, right? So now we increase the area, right? So then the load bearing capacity, everything is now much better than your contact point. Suppose if it's a 2-point contact, 2-point contact is a line contact, right? So then we spread it to over a larger distance, right? Right. So many times when we talk about like 3-point contact, or in machining also, what do we realize? That you don't go for like designing something like this, or suppose if so one component and the other component, right? So you know that this should be like this. You never do like that, because the machining effort, the flatness, surface quality, everything you have to maintain from here to here. What you do is, if you have this kind of thing, you make a groove. So then you know that, okay, the important points are only these two. Then you can make it very accurate, right? Flatness, everything, and this is enough, right? Because it will be resting on this point. If it's like this, you don't know where you are resting at these 2 points or these 2 points, right? So it's always better to make it deterministic. Suppose if it's just you want to have point contact, in that case you may just go for like this kind of contact. So these are semi-kinematic. Yes, so I think the time is up, so maybe we stop here and then we discuss further. Okay.